Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With 200 gigabit private networking, scalable shared block storage, and a 40 gigabit public network, you've got everything you need to run a fast, reliable, and bulletproof data platform. If you need global distribution, they've got that covered too, with worldwide data centers, including new ones in Toronto and Mumbai. And for your machine learning workloads, they just announced dedicated CPU instances. Go to dataengineeringpodcast.com/Linode, that's Linode today to get a $20 credit and launch a new server in under a minute. And don't forget to thank them for their continued support of this show. And listen, I'm sure you work for a data-driven company. Who doesn't these days? Does your company use Amazon Redshift? Have you ever groaned over slow queries or are just afraid that Amazon Redshift is going to fall over at some point? Well, you've got to talk to the folks over at Intermix.io. They have built the missing Amazon Redshift console. It's an amazing analytics product for data engineers to find and rewrite slow queries, and it gives actionable recommendations to optimize data pipelines. WeWork, Postmates, and Medium are just a few of their customers. Go to dataengineeringpodcast.com/intermix today and use promo code DEP at signup to get a $50 discount. And you listen to this show to learn and stay up to date with what's happening in databases, streaming platforms, big data, and everything else you need to know about modern data management. For even more opportunities to meet, listen, and learn from your peers, you don't want to miss out on this year's conference season. We have partnered with organizations such as O'Reilly Media, Dataversity, Corinium Global Intelligence, and Data Council. Upcoming events include the O'Reilly AI Conference, the Strata Data Conference, the combined events of the Data Architecture Summit and Graph Forum, and Data Council in Barcelona. Go to dataengineeringpodcast.com/conferences to learn more about these and other events and take advantage of our partner discounts to save money when you register today. Your host is Tobias Macey, and today I'm interviewing Simon Crosby about Swim.ai, the data fabric for the distributed enterprise. So, Simon, can you start by introducing yourself?
Hi, I'm Simon Crosby. I am the CTO, I guess, of long duration. I've been around for a long time, and it's a privilege to be with the Swim folks who have been building this fabulous platform for fast streaming data for about 5 years.
And do you remember how you first got involved in the area of data management?
Well, I have a PhD in applied mathematics and probability. So I am kind of a not data management guy. I'm an analysis guy. I like what comes out of streams of data and what inference you can draw from it. So my background is more on the analytical side. And then along the way, I started picking up how to build big infrastructure for IT.
And now you have taken up the position as CTO for Swim.ai. I'm wondering if you can explain a bit about what the platform is and how the overall project and business got started.
Sure. So here's the problem. We're all reading all the time about these wonderful things that you can do with machine learning and streaming data and so on. It all involves cloud and other magical things. And in general, most organizations just don't know how to make head or tail of that. For a bunch of reasons, it's just too hard to get there. So if you're an organization with assets that are chirping out lots of data, and that could be a bunch of different types, you probably don't have the skill set in-house to deal with a vast amount of information. And we're talking about boundless data sources here, things that never shut up. And so to deal with these data flow pipelines, to deal with data itself, to deal with the learning and inference that you might draw from that, and so on. And so enterprises today have a huge skill set challenge. There is also a cost challenge because today's techniques related to drawing inference from data in general resolve with, in large, expensive data lakes, either in-house or perhaps in the cloud. And then finally, there's a challenge with the timeliness within which you can draw an insight. And most folks today believe that you store data and then you think about it in some magical way and you draw inference from that. And we're all suffering from the Hadoop Cloudera, I guess, after effects. And really, this notion of storing and then analyzing needs to be dispensed with in terms of fast data. Certainly for boundless data sources that will never stop, it's really inappropriate. So when I talk about boundless data, we're going to talk about data streams that just never stop. And we're also going to talk about the need to derive insights from that data on the fly, because if you don't, something will go wrong. So it's of the type that would stop your car before you hit the pedestrian in the crosswalk, that kind of stuff. So for that kind of data, there's just no chance to store the data on a hard disk and then learn.
And how would you differentiate the work that you're doing with the Swim.ai platform and the SwimOS kernel from things that are being done with tools such as Flink or other streaming systems such as Kafka that has now got capabilities for being able to do some limited streaming analysis on the data as it flows through, or also platforms such as Wallaroo that are built for being able to do stateful computations on data streams?
So first of all, there have been some major steps forward, and anything we do, we stand on the shoulders of giants. Let's start off with distinguishing between the large enterprise skill set that's out there and the cloud world. And all the things you mentioned live in the cloud world. So at that rough first distinction, most people in the enterprise, when you say Flink, wouldn't know what the hell you're talking about. Okay. Similarly, Wallaroo or anything else. They just wouldn't know what you're talking about. And so there is a major problem with the tools and technologies that we have built for the cloud. Really for a lot of cloud native applications and the majority of enterprises who they're stuck with legacy IT and application skill set, and they're still coming up to speed with the right thing to do. And to be honest, they're getting over the headache of Hadoop. So then if we talk about the cloud native world, there is a fascinating distinction between all of the various projects which have started to tackle streaming data, and there have been some major some major progress there, which I'd be delighted to point out. Swim being one of them, and happy to go into each one of those projects in detail as we go forward. The key point being that first and foremost, the large majority of enterprises just don't know what the heck to do.
And then within your specific offerings, there is the Data Fabric platform, which you're targeting for enterprise consumers. And then there's also the open source kernel of that in the form of SwimOS. I'm wondering if you can provide some explanation as to what are the differentiating factors between those two products and the sort of decision points along when somebody might want to use one versus the other.
Yeah, let's cut it first at the distinction between the application layer and the infrastructure needed to run a large distributed data flow pipeline. And so for Swim, all of the application layer stuff, then there's everything you need to build an app, is entirely open source. Some of the capabilities that you want to run a large distributed data flow pipeline are proprietary. And that's really just because we're building a business around this. We plan to open source more and more features over time.
And then, as far as the primary use cases that you are enabling with the Swim platform and some of the different ways that enterprise organizations are implementing it, what are some of the cases where using something other than Swim, either the OS or the data fabric layer, would be either impractical or intractable if they were trying to use more traditional approaches such as Hadoop, as you mentioned, or data warehouse and more batch-oriented workflows?
So let's start off describing what Swim does. Can I do that? That might help. In our view, it's our job to build the pipeline and indeed the model from the data. Okay, so Swim just wants data, and from the data we will automatically build this stateful data flow pipeline. And indeed, from that, we will build a model of arbitrarily interesting complexity, which allows us to solve some very interesting problems. Okay, so the Swim perspective starts with data because that's where our customer's journey starts. They have lots and lots of data, they don't know what to do with it. And so the approach we've taken at Swim is to allow the data to build the model. Now, you would naturally say that's impossible. In general, what's required is some ontology at the edge, which describes the data. You could think of it as a schema, in fact, basically to describe what data items mean in some sort of useful sense to us as modelers. But then, given data, Swim will build that model. So let me give you an example. Given a relatively simple ontology for traffic equipment, so pedestrian lights, the loops on the road, the lights, and so on, Swim will build a model which is a stateful digital twin, as it were, for every sensor, every source of data, which is running in concurrently in some distributed fabric and processes its own raw data and statefully evolves. Okay, so simply given that ontology, Swim knows how to build stateful, concurrent little things we call web agents. Actually, I'm using that term. I guess the same as digital twin. And these are concurrent things which are going to statefully process raw data and represent that in a meaningful way. And the cool thing about that is that each one of these little digital twins exists in a context, a real world context that Swim is going to discover for us. So, for example, an intersection might have 60 to 80 sensors. So there's a notion of containment. But also, intersections are adjacent to other intersections in the real world map. And so that notion of adjacency is also a real world relationship. And in Swim, this notion of a link allows us to express the real world relationships between these little digital twins. And linking in Swim has this wonderful additional property, which is to allow us to express essentially a sub. So in Swim, there is never a pub, but there is a sub. And if something links to something else, so if I link to you, then it's like LinkedIn for things. I get to see the real-time updates of in-memory state stored by that digital twin. So digital twins that are linked to other digital twins, courtesy of real-world relationships, such as containment or proximity. We can even do other relationships like correlation. Also link to each other, which allows them to share data. And sharing data allows interesting computational properties to be derived. For example, we can learn and predict. Okay, so job one is to define this ontology. Swim then goes and builds a graph of digital twins, which is constructed entirely from the data. And then the linking happens as part of that, and that allows us to then construct interesting computations. Is that useful?
Yes, that's definitely helpful to get an idea of some of the use cases and some of the ways that the different concepts within Swim work together to be able to build out to what a sort of conceptual architecture would be for an application that would utilize Swim?
So the key thing here is I'm talking about an application. Let's just say the application is to predict the future traffic in any city, or what's going to happen in the traffic area, right? Now, I could do that for a bunch of different cities. What I can tell you is I need a model for each city. And there are two ways to build a model. One way is I get a data scientist to go and build me a model. Maybe they train it and do a whole bunch of other things. And I'm going to have to do this for every single city where I want to use this application. The other way to do it is to build the model from the data. And that's the Swim approach. So what Swim does is simply, given the ontology, build these little digital twins, which are representatives of the real world things, get them to statefully evolve, and then link to other things to represent real world relationships. And then suddenly, hey presto, you have built a large graph, which is effectively the model that you would have had to have a human build otherwise, right? So it's constructed in the sense that in any new city you go to, this thing is just going to unbundle, and just given a stream of data, it will build a model which represents the things that are the sources of data and their physical relationships. Does that make sense?
Yeah, and I'm wondering if you can expand upon that in terms of the type of workflow that a developer who is building an application on top of Swim would go through, as far as identifying what those ontologies are and defining how the links will occur as the data streams into the different nodes in the SwimOS graph.
So the key point here is that we think that we can do, I don't know, we can build like 80% of an app, okay, from the data. And that is, we can find all of the big structural, all structural properties of relevance in the data, and then let the application builder drop in what they want to compute. And so let me try and express this slightly differently. Job one, we believe, is to build a model of these stateful digital twins, which almost mirror their real world counterparts. So at all points in time, their job is to represent the real world as faithfully and as close to real time as they can in a stateful way, which is of relevance to the problem at hand. Okay, so rather than voltages, I'm going to have a red light. Okay, something like that. And the first problem is to build this set of digital twins which are interlinked, which represent the real world being studied. Okay, and it's important to separate that from the application layer component of what you want to compute from that. So frequently we see people making the wrong decision. That is hard coupling the notion of prediction or learning or any other form of analysis into the application in such a way that any change requires programming. And we think that that's wrong. So job one is to have this faithful representation of a real-time world in which everything evolves its own state whenever its real-world twin evolves, and it evolves statefully. And then the second component of this, which we do on a separate time scale, is to inject operators which are going to then compute on the states of those things at the edge. Right? So we have a model which represents the relationships between things in the real world. It's attempting to evolve as close as possible to real time in relationship to the real world twins, and it's reflecting its links and so on. But the notion of what you want to compute from it is separate from that and decoupled. And so the second step, which is an application or building an application right here, right now, is to drop in an operator which is going to compute a thing from that. So you might say, cool, I want every digital twin of every intersection to compute, to be able to learn from its own behavior and predict. That's one thing. Or you might say, I want to compute the average wait time of every car in the city. That's another thing. So the key point here is that computing from these rapidly evolving worldviews is decoupled from the actual model of what's going on in that world at any point in time. So Swim reflects that decoupling by allowing you to bind operators to the model whenever you want. Okay? And by whenever you want, I mean you can write them in code in bits of Java or whatever, but also you can write them in blobs of JavaScript or Python and dynamically insert them into a running model. Okay, so let me make that one concrete for you. I could have a deployed system, which is a model, a deployed graph of digital twins, which are currently mirroring the state of Las Vegas. And dynamically, a data scientist says, let me compute the average wait time of red cars at these intersections, and drops that in as a blob of JavaScript attached to every digital twin for an intersection. That is what I mean by an application. And so we want to get to this point where the notion of application is not something deeply hidden in somebody's, notebook or Jupyter notebook or in some programmer's brain and they quit and wandered off to the next startup 10 months ago. An application is what I want to know right now, dropped into a running model.
So the way that sounds like to me is that Swim essentially acts as you deploy the infrastructure layer to ingest the data feeds from these sets of sensors, and then it will automatically create these digital twin objects to be able to have some digital manifestation of the real world so that you have a continuous stream of data and how that's interrelated. And then it sort of flips the order of operations in terms of how the data engineer and the data scientist might work together, where the way that most people are used to, you will ingest the data from these different sensors, bundle it up, and then hand it off to a data scientist to be able to do their analyses. They generate a model and then hand it back to the data engineer to say, okay, go ahead and deploy this and then see what the outputs are, where instead the Swim platform essentially acts as the delivery mechanism and the interactive environment for the data scientist to be able to experiment with the data, build a model, and then get it deployed on top of the continuously updating live stream of data, and then be able to have some real world interaction with those sensors in real time as they're doing that, to be able to feed that back to say, okay, red cars are waiting 15% longer than other cars at these two intersections. So now I want to be able to optimize our overall grid, and that will then feed back into the rest of the network to have some physical manifestation of the analysis that they're trying to perform to try and maybe optimize
Bingo.
the overall traffic
and
flow.
So there are some consequences for that. First of all, every algorithm has to compute stuff on the fly. So if you look at the kind of store and then analyze approach to big data type learning or any training or anything else, you have all the bits, and here you don't. And so every algorithm that is part of Swim is coded in such a way as to continually process data. And that's fundamentally different to most frameworks. Okay, so for example, the learn and predict cycle is one. You mentioned training and so on. That's very interesting. But training implies that I collect and store some training data, and that it's complete and useful enough to parameterize a model that I can then hand back. What if it isn't? And so in Swim, we don't do that. I mean, we can if you want. If you have a pre-built model, that's no problem for us to feed data to. But instead, in Swim, the input vector, say, to a prediction algorithm, say DNN, is precisely the current state of the digital twins for some bunch of things, right? Maybe the set of sensors in the neighborhood of an intersection. And so this is a continually varying real world triggered scenario in which real data is fed through the algorithm but is not stored anywhere. So everything is fundamentally streaming. So we assume that data streams continually, and indeed the output of every algorithm streams continually. So what you see when you're computing the average is the current average. Okay, when you're looking for heavy hitters, what you see is the current heavy hitters. All right, and so every algorithm has its streaming twin, I guess, and part of the art in the swim context is reformulating the notion of analysis into a streaming context so that you never expect a complete answer because there isn't one. There's just what I've seen until now. Okay, and what I've seen until now has been fed through the algorithm, and this is the current answer. And so every algorithm computes and streams. And so the notion of linking, which I described earlier for Swim, between digital twins, say, applies also to these operators, which effectively would link to things they want to compute from, and then they would stream the results. Okay, so if you link to them, you see a continued update. And for example, that stream could be used to feed a Kafka implementation, which would serve a bunch of applications. Kafka, the notion of streaming is pretty well understood. So we can feed other bits of the infrastructure very well, but fundamentally everything is designed to stream.
Yeah, it's definitely an interesting approach to the just overall workflow of how these analyses work. And one thing that I'm curious of is how data scientists and analysts have found working with this platform in terms of ways that they might be used to.
You're interested in what data scientists would view or how they view this. To be honest, in general, with surprise, um, our experience to date has been largely with people who don't know what the heck they're doing in terms of data science. So they're trying to run an oil rig more efficiently. They have, whatever, 10,000 sensors, and they want to make sure this thing isn't going to blow up. Okay, so they tend to be heavily operationally focused folks. They're not data scientists. They never could afford one. And they don't understand the language of data science or have the ability to build cloud-based pipelines that you and I might be familiar with. So these are folks who effectively just want to do a better job given this enormous stream of data that they have. They believe they have something in the data. They don't know what that might be, but they're keen to go and see. Okay. And so those are the folks we spent most of our time with. I'll give you a funny example if you'd like.
Sure, that would be
Sure,
illustrative.
that would be
Okay.
illustrative.
So we work with a manufacturer of aircraft, and they have a very large number of RFID tag parts and equipment too. And so if you know anything about RFID, you know it's pretty useless stuff. It's built from about 10 years ago and 20 years ago. And so what they were doing is from about 2,000 readers, taking about 10,000 reads a second. And each one of these reads is simply being written into an Oracle database. At the end of the day, they try and reconcile this all with whatever parts they have and where everything is and so on. And the Swim solution to this is entirely different. It gives you a good idea of why we care about modeling data or think about data differently. we simply build a digital twin for every tag. The first time it's seen, we create one, and then they haven't been seen for a long time. They just expire. And whenever a reader sees a tag, it simply says, "Hey, I saw you, and this was the signal strength." Now, because tags get seen by multiple readers, each digital twin of a tag does the obvious thing. It triangulates from the readers. Okay, so it learns the attenuation in different parts of the plant, which is a very simple niche. That's the word "learn" there is rather stretched. It's a pretty straightforward calculation, and then suddenly it can work out where it is in 3 space. So instead of an Oracle database or a database full of tag reads and lots and lots of post processing, you end up with a couple of Raspberry Pis, and each one and these Raspberry Pis, have millions of these little tags running in there, and you can ask any one of them where it is. Okay, and then you can do even more. You can say, "Hey, show me all the things within 3 meters of this tag." Okay, and that allows you to see components being put together into real physical objects, right? So as a fuselage gets built of the engine or whatever it is. And so a problem which was tons of infrastructure and tons of tag reads got turned into 2 Raspberry Pis worth of stuff, which kind of self-organized and into a form which could feed real-time visualization and controls around what bits of infrastructure were where. Okay. Now that was transformative for this outfit, which quite literally hadn't thought of tackling the problem in this way. Does that make sense?
Yeah, that's definitely a very useful example of how this technology can flip the overall order of operations and just the overall capabilities of an organization to be able to answer useful questions. And the idea of going from, as you said, an Oracle database full of all these just rows and rows of records of this tag got read at this point in this location, and then being able to actually get something meaningful out of it as far as this part is in this location in the overall reference space of the warehouse is definitely transformative, and probably gave them weeks or months worth of additional time in terms of lead time for being able to predict problems or identify areas for potential optimization.
Yeah, and I think we saved them $2 million a year. Let me tell you what, from this tale come 2 interesting things. First of all, if you show up at a customer with something running on Raspberry Pi, you can't charge them $1 million. Okay, that's lesson 1. Lesson 2 is that the volume of the data is not relevant or not related to the value of the insight. Okay, I mentioned traffic earlier. In the city of Las Vegas, we get about between 50 and 60 terabytes per day of the traffic infrastructure. And every intersection, every digital twin of every intersection in the city predicts 2 minutes into its future. Okay. And those insights are sold in an API in Azure to customers like Audi and Uber and Lyft and whatever else. Okay. Now, that's a ton of data. Okay. It's just you couldn't even think of where to put in your cloud. But the value of the insight is relatively low. That is, the total amount of money I can extract from Uber per month per intersection is low. All right. By the way, all this stuff is open source. You can go and grab it and play and hopefully make your city better. So what from that you can gather that it's not of high enough value for me to do anything other than say, go grab it and run. So vast amounts of data and relatively important, but not commercially relevant value.
And another aspect of that case in particular is that despite this volume of data, it might be interesting for being able to do historical analyses, but in terms of the actual real world utility, it has a distinct expiration period where you have no real interest in the sensor data as it existed an hour ago because that has no particular relevance on your current state of the world and what you're trying to do with it at this point in time.
Yeah, you have historical interest in the sense of wanting to know if your predictions were right or wanting to know about it for traffic engineering purposes, which runs on a slower time scale. So some form of bucketing or whatever, some more terse form of recording is useful. And sure, that's easy, but you certainly did not want to record it at the original data rate.
And then going back to the other question I had earlier when we were talking about the workflow of an analyst or a data scientist pushing out their analyses live to these digital twins and potentially having some real world impact, I'm curious if the Swim platform has some concept of a dry run mode where you can deploy this analysis and see what the output of it is without it and see maybe what impact it would have without it actually manifesting in the real world for cases where you want to ensure that you're not accidentally introducing error or potentially having a dangerous outcome, particularly in the case that you were mentioning of an oil and gas rig.
Yeah, so I'm with you 100%. Actually, everything we've done thus far has been open loop in the sense that we're informing a human or another application, but we're not directly controlling the infrastructure. And the value of a dry run would be enormous. You can imagine in those scenarios. But thus far, we don't have any use cases that we can report of using Swim for direct control. We do have use cases where on a second by second basis, we are predicting whether machines are going to make an error as they build PCBs for servers and so on. But again, what you're doing is you're calling Freddy to come over and fix the machine. You're not trying to change the way the machine behaves.
And now, digging a bit deeper into the actual implementation of Swim, I'm wondering if you can talk through how the actual system itself is architected and some of the ways that it has evolved as you have worked with different partners to deploy it into real world environments and get feedback from them, and how that has affected the overall direction of the product roadmap.
So Swim is a couple of megabytes of Java extensions. Okay. So it's extremely lean. We tend to deploy in containers using a GraalVM. So it's very small. We can run in, probably 100 megabytes or so. And so people tend to think of, when people tend to think of Edge, they tend to think of running in the Edge gateways or things. We don't really think of Edge in that way. And so an important part of defining Edge, as far as we're concerned, is simply gaining access to streaming data. We don't really care where it is. But Swim is small enough to get on limited amounts of compute towards the physical edge. And the the product has evolved in the sense that originally it wasn't a way of building applications for the edge, and you'd sit down and write them in Java and so on. Laterally, this ability to simply let the application data, or let the data build the app, or most of the app, came upon us in response to customer needs. But Swim is deployed typically in containers, and for that we have, in our current release, relied very heavily on the Azure IoT Edge framework, and that is magical, to be quite honest, because we can rely on Microsoft machinery to deal with all of the painful bits of deployment and lifecycle management for the code base and the application as it runs. These are not things that we are really focused on. What we're trying to do is build a capability which will respond to data and do the right thing for the application developer. And so we are fully published in the Azure IoT hub, and you can download us and get going and manage us through the lifecycle that way. And so in several use cases now, what we're doing is we are used to feed fast timescale insights at the physical edge. We are labeling data and then dropping it into Azure ADLS Gen 2 and feeding insights into applications built in Power BI. Okay, so it just for the sake of machinery, using the Azure framework for management of the IoT edge. And by the way, I think IoT edge is about the worst possible name you could ever pick, because all you want is a thing to manage the lifecycle management of a capability which is going to deal with fast data. Whether it's at the physical edge or not is immaterial. But that's basically what we've been doing, is relying on Microsoft's fabulous lifecycle management framework for all that. We plug into the IoT hub and all of the Azure IoT or Azure services generally for back-end things, which enterprises love.
And then another element of what we were discussing in the use case examples that you were describing, particularly, for instance, with the traffic intersections, is the idea of discoverability and routing between these digital twins as far as how they identify the cardinality of which twins are useful to communicate with and establishing those links, and also at the networking layer, how they handle network failures in terms of communication and ensuring that if there is some sort of fault that they're able to recover from it.
Swim builds, let's talk about two layers. One is the app layer and the other one is the infrastructure which is going to run this effectively this distributed graph. And so Swim is going to build this graph for us from the data. What that means is the digital twin, by the way, we technically call these web agents. These little web agents are going to be distributed somewhere in a fabric of physical instances, and they may be widely geographically distributed. And so there is a need, nonetheless, at the application layer for things which are related in some way, linked physically or in some other way, to be able to link to each other. That's the Swim equivalent of a sub. And so links require that objects, which are these digital twins, have the ability to inspect each other's data, right? They're members. And of course, if something is running on the other side of the planet and you're linked to it, how on earth is that going to work? So we're all familiar with object-oriented languages and objects in one address space. That's pretty easy. We know what an object handle or an object reference or a pointer or whatever, we get it. But when these things distribute, that's hard. And so in Swim, if you're an application programmer, you would simply use object references, but these resolve to URIs. So in practice, at runtime, the linking, that is when I link to you, I'll link to a URI. And that link, once resolved by Swim, enables a continued stream of updates to flow from you to me. And if we happen to be on different instances, that is running in different address spaces, then that will be over a mesh, over a direct WebSockets connection between your instance and mine. And so in any Swim deployment, all instances are interlinked. So each link to each other using a single WebSockets connection. And then these links permit the flow of information between linked digital twins. And what happens is whenever a change in the in-memory state of a linked digital twin happens, what happens is that its instance then streams to every other linked object and update to the state for that thing, right? So what's required is, in effect, a streaming update to JSON, right? Because if we're going to record our model in some form of like JSON state or whatever, we would now need to be able to update little bits of it as things change. And so we use a protocol called Warp for that. And that's a swim capability which we've open sourced. And what that really does is bring streaming to JSON, right? Streaming updates to parts of a JSON model. And then every instance in Swim maintains its own view of the whole model. So as things stream in, the local view of the model is changed, but the view of the world is very much one of a consistency model based on whatever happens to be executing locally and whatever needs to view state. So it's an eventually consistent data model in which every node eventually learns the entire thing. And generally, eventually here means, a link away from real time, right? So a link's delay away from real time.
And then the other aspect of the platform is the statefulness of the computation. And as you were saying, that state is eventually consistent, dependent on the communication delay between the different nodes within the context graph. And then in terms of data durability, one thing I'm curious of is the length of state, or sort of the overall buffer that is available. I'm guessing is largely dependent on where it happens to be deployed and what the physical capabilities are of the particular node. And then also, as far as persisting that data for maybe historical analysis, my guess is that relies on distributing the data to some other system for long-term storage. And I'm just wondering what the overall sort of pattern or paradigm is for people who want to be able to have that capability.
Oh, those are great questions. So, in general, then we're going from some horrific raw data form on the wire from the original physical thing to, something much more efficient and meaningful in memory, and generally much more concise. So we get a whole ton of data reduction that way. And so though Swim is focused on streaming, we don't stop you storing your original data if you want to. You might just have to have disks everywhere or whatever. The key thing in Swim is we don't do that on the hot path. Okay, so things change their states in memory and maybe compute on that. And that's what they do first and foremost. And then we lazily throw things out to disk because disks happen slowly relative to compute. And so typically what we end up storing is the semantic state of the context graph, as you put it, not the original data. That is, for example, in the traffic world, we store things like this light turned red at this particular time, not the voltage on all the registers in the light. And so you get massive data reduction. And that form of data is very amenable to storage in the cloud, say, or somewhere else. And it's even affordable at reasonable rates. So the key thing for Swim and storage is you can remember as much as you want, as much as you have space for locally, and then storage in general is not on the hot path. It's not on the compute and stream path, and generally we're getting huge data reductions for every step up the graph we make. So, for example, if I go from all the states of all the traffic sensors to predictions, then I've made a very substantial reduction in the data amount anyway, right? So as you move up this computational graph, you reduce the amount of data that you're going to have to store. And it's up to you to really pick what you want to store.
In terms of your overall experience working as the CTO of this organization and shepherding the product direction and the capabilities of this system, I'm wondering what you have found to be some of the most challenging aspects, both from the technical and business sides, and some of the most useful or interesting or unexpected lessons that you've learned in the process.
So what's hard is that the real world is not the cloud native world. So we've all seen fabulous examples of Netflix and Amazon and everybody else doing cool things with data. They do. But if you're an oil company and you have a rig out at sea, you just don't know how to do this. So, we can come at this with whatever skill sets we have. What we find is that the real world, the large enterprises of today, are still acres behind the cloud native folk. And that's a challenge. Okay, so getting to be able to understand what they need, because they still have lots of assets which are generating tons of data, is very hard. Second, this notion of edge is continually confusing. And I mentioned previously that I would never have chosen IoT edge as, for example, the Azure name, because it's not about IoT, or maybe it is. But let me give you two examples. One is traffic lights, say, physical things. It's pretty obvious that what the notion of edge is, it's physical edge. But the other one is this: we build a real-time model for millions, tens of millions of handsets for a large mobile carrier in memory, and evolves all the time, right, in response to continually receive signals from these devices. There is no edge. That is, it's data and derives over the internet, and we have to figure out where the digital twin for that thing is and evolve it in real time. Okay? And there is no concept of a network that we know, or a physical edge, and the data traveling over that. We just have to make decisions on the fly and learn and update this model. So for me, edge is the following thing. Edge is stateful, and cloud is all about rest. Okay, so what I would say is the fundamental difference between the notion of edge and the notion of cloud that I would like to see broadly understood is that whereas REST and databases made the cloud very successful, in order to be successful with this boundless streaming data, statefulness is fundamental, which means rest goes out the door. And we have to move to a model which is streaming based and stateful computation.
And then in terms of the future direction, both from the technical and business perspective, I'm wondering what you have planned for both the enterprise product for Swim.ai as well as the open source kernel in the form of SwimOS.
From an open source perspective, we don't have the advantage of having come out of a LinkedIn or something where we were built and used at scale. And we're coming out of a startup. What we think we built is something which is of phenomenal value, and we're seeing that grow. And our intention is to continually feed that community as much as it can take. And we're just getting more and more stuff ready for open sourcing and handing out. So we want to see our community go and explore new use cases for using this stuff, and are totally dedicated to empowering our community. From a commercial perspective, we are focused on a world which is edge. And the moment you say that to people, they tend to get an idea of physical edge or something in their heads. And then, very quickly you can get put in a bucket of IoT. I gave an example of say, building a model in real time in AWS for, a mobile customer. Our intention is to continue to push the bounds of what edge means, and to enable people to build stream pipelines for massive amounts of data easily, without complexity and without the skill set required to invest in these traditionally fairly heavyweight pipeline components such as Beam and Flink and so on, to enable people to get insights cheaply and to make the problem of dealing with new insights from data very easy to solve.
And are there any other aspects of your work on SwimAI and the space of streaming data and digital twins that we didn't discuss yet that you'd like to cover before we close out the show?
I think we've done a pretty good job. I think there are a bunch of parallel efforts, and that's all goodness. That is one of the harder things has to be to get this notion of statefulness more broadly accepted. And I see the folks from Lightbender out there pushing their idea of this, stateful functions as service, and really these are stateful lambdas. And there are others out there too. So for me, step number one is to get people to realize that if we're going to tame boundless data, that REST and databases are going to kill us. Okay, there is so much data and the rates are so high that you simply cannot afford to use a stateless paradigm for processing. You have to do things statefully, because forgetting the context every time and having to look it up is just too expensive.
For anybody who wants to follow along with you and get in touch and keeping track of what you're up to, I'll have you add your preferred contact information to the show notes. And as a final question, I would just like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
Well, there isn't much tooling, really, to be perfectly honest. There are a bunch of really fabulous open source code bases and experts in their use, but that's far from tooling. And then there is, I guess, an extension of the Power BI downwards world, which is something like the monster Excel spreadsheet world, right? So you find all these folks who are pushing that kind of end user model of data, doing great things, but leaving a huge gap between the consumer of the insight and the data itself. That is, assuming the data is already there in some good form and can be put into a spreadsheet or whatever it happened to be. So there's this huge gap in the middle, which is, how do we build the model? What does the model tell us just off the bat? How do we do this reconstructively in large number of situations? And then how do we dynamically insert operators which are going to compute useful things for us on the fly in running models?
Well, thank you very much for taking the time today to join me and discuss the work that you've been doing on the Swim platform. It's definitely a very interesting approach to data management and analytics, and I look forward to seeing the direction that you take it in the future. So I appreciate your time on that, and I hope you enjoy the rest of your day.
Thanks very much. It's been great to be here.
Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.